Welcome everyone to this Europractice webinar. My name is Maria Martinez Balado. I'm a program manager at imec and Europractice, and I will be your host today. Today, as you know, we continue the Compound Semiconductor webinar series. As you may remember, this series started already in 2023 in November, and the first episode was an introduction to compound semiconductor materials. We saw a bit of applications of these technologies and a little bit of the market overview. After that episode, we have different ones, each one dedicated to a single technology. In December last year, we had an episode dedicated to 4H silicon carbide CMOS technologies for harsh environment applications that was given by Fraunhofer IISB. And last week, we had another episode dedicated to gallium arsenide technologies for power and low noise RF amplification given by UMS. The recordings of these webinars and all the others we have done in Europractice are already in our YouTube channel, and I invite all of you to go there after this episode and check your favorite webinars. So, and by the way, the session of today will be also there in a few days. So, as you can see in the slide that is sharing in the screen, we have 3 more webinars to go. In the coming weeks, we will have episodes in indium phosphide for photonic integrated circuits and silicon germanium by CMOS technologies. But today, the focus will be on gallium nitride technologies, and we will explore the possibilities of this material in 3 different domains: LED, power, and RF. And to guide us through all this, both from the technical perspective, but also from the commercial one, we have here our speaker, Maritza Tangarife Ortiz, that is present in this virtual stage. And it is my pleasure to introduce her briefly to all of you. So Maritza was born in Colombia, and she received her diploma in physics engineering from the National University of Colombia. And after that, she moved to Germany to pursue her master in photonics from the University of Jena in Germany. After graduating, she worked as a researcher in different institutes of Germany and Colombia in different topics ranging from optical design, holography, or laser metrology. She joined imec in 2018 as a tape-out engineer for the Silicon Photonics MPW service. And after more or less a year, she switched to gallium nitride integrated circuit and PW service, which she is leading nowadays, being responsible for both the business part and as well as the tape-out activities. So with this, I have concluded my part, and it's time for you to enjoy the presentation. I wish you all a very nice webinar, and Maritza, when you want, the floor is yours. Maritza, you are muted, sorry.
Thank you very much, Maria, for the introduction. Just give me a moment. I will. Yes. Okay. No, thanks for the introduction. Just some context on the change from the photonics to the GaN to the power electronics environment. Well, no, it's as a part of the activities in different businesses at imec. Well, I started to interact more with different groups and gain some interest in these new technologies. And with previous knowledge, well, some semiconductor knowledge, and also on the business side, in our group, we started this project of GaN MPWs, and that's how we ended up, already 5 years working in the power electronics industry. So that's what I wanted to comment. So just a sec. Okay, here is visible laser. So to the audience, well, thank you very much for your attendance. As mentioned already, well, this is a Compound Semiconductor series organized by Europractice, and we'll be talking about gallium nitride, a compound material that is gaining a lot of relevance in the semiconductor industry, and it has impacted different technology fields that we will briefly check today, as power conversion, advanced RF, and LEDs. So if we look at the contents, well, we must consider today that we are counting with a very broad audience. So we will start aligning with some fundamental physical concepts. Later on, we'll start introducing, let's say, we will see how the entrance of gallium nitride was into the semiconductors world. So we will present, let's say, the baselines of the LED technology. Later on, we'll come to a more technical. Just a second. Later on, we'll come with an overview of the market and industrial panorama for GaN and some adoption challenges. And finally, I will comment about the GaN platforms that are available via your practice, which are imec and UMS. And I will show some demonstrator that some customers have fabricated with using these technologies. So let's check the basics. Well, so this is probably a diagram we are already very familiar. But as for alignment, well, let's start. We refer to silicon carbide, gallium nitride, and other materials as wide bandgap materials. But what does it mean? So when we look at the semiconductors, we model them in terms of the electronic band theory for solids. So when we have the crystalline solids, electrons occupy a large number of energy levels, yeah, and we group them in. Well, they are grouped into nearly continuous energy bands. So the width and spaces of the energy bands differs considerably with the properties of the material. So at higher level, just a moment, let me shift this here. Well, at higher energy levels within the atom, we have two distinct bands. We name them the valence band and the conduction band. And we use those bands of energy to define a band gap for the material. So how do we understand this? Well, in the valence band, the electrons form fixed localized bonds in the atoms, and they have a lower energy level compared to the electrons in the conduction band, which are highly movable electrons. So when electrons in the valence band, here the black ones, let's say, receive enough energy, they pass the conduction band, where they are able to start carrying the charge through a material. So we call them their free carriers. What can happen here here on the conduction band? Well, the electrode, when the electrons break out of the valence band, they leave behind a positively charged holes. If you remember well, the electrons are negatively charged. And as for the materials of interest, we must say that the band gaps in semiconductors are small, but they are also finite, so they are very sensitive to temperature. Of course, well, most of the semiconductor devices that we use are designed so that the application of a voltage is required to produce the changes in the electron distribution between the valence and the conduction bands. So what do we want to have in a semiconductor? In a semiconductor, we would like to have a wide bandgap. What does it mean? That the material can operate at higher voltages and at higher frequencies. We would like to have also a material which has a high tolerance for temperatures, so it remains stable and it can operate at more demanding environments. We want a material that can stand high electric fields with the smallest dimension, so we want to reduce the size. That is quite a self-evident in a way. And we want to have high electron mobility. What does it mean? We want that the electrons can travel within the material at high speeds and with minimal scattering. So what does it mean? That we have fewer losses or fewer energy dissipation via heat. So if we come to to compare now the desired properties of GaN with silicon carbide and silicon, we can see in this table that, well, the bandgap for GaN is 3.49 electrovolts, which is higher than silicon carbide, but it is also far higher than silicon alone, which is 1.1. And this is, and we must mention here that this bandgap is direct. What do I mean? That the transition from the covalence to the conduction band is immediate, that you don't have, let's say, steps in the transition where you would lose energy via, you will be dissipating energy. So the more straightforward the bandgap, there will be fewer losses associated to intermediate states. Yeah, so we have here, GaN has a bandgap 3 times wider than silicon, so it can operate at higher voltages and frequencies than silicon. If we look at the electron mobility, this is slightly slower than silicon, but still higher than silicon carbide. So let's say electrons in GaN can still travel at a comparable speed with minimal losses. If we look at the thermal thermal conductivity, it is quite evident that silicon carbide outperforms GaN and silicon. So it means silicon carbide is more effective at transporting heat and higher tolerance to temperature and harsh environments. And in terms of the critical electrical field, well, we have that basically silicon carbide and GaN are 10 times bigger, it's 10 times higher than the one of silicon. So it means it's possible to have smaller devices, which is of high interest for industry. And okay, well, having checked these concepts quickly, in the next chapter, we will talk about other physical phenomena related to GaN for LED technologies. Okay, so considering the material properties, we start discussing now the technologies where GaN has had a relevant impact. For historical reasons, I will start with LED technology, because this is the one that initially brought attention towards GaN. So we have that LED stands for Light Emitting Diode. So in principle, what we have is a basic diode. We have a basic diode, and but roughly speaking, we have that a diode is made up of, let's say, a sandwich of two materials standing on a substrate. In this case, on the right case, we have the material is specifically doped to donate electrons. We call the N-type material. And if we look to the right, we have a material that is doped to accept electrons. We call it P-type layer. And what happens that in the interface between these two materials, we have what we call a p-n junction. Well, with this configuration, go here to the right, when we apply the specific electric field to this junction, to the p-n junction, what happens? That the donated electrons and the electron holes recombine. So what we have is the result. What we have as a result of this recombination is the emission of light that we have on LEDs. And material-wise, this is relevant because depending on the material or combination of materials in the junctions, we will have a specific type of light. So the changes in energy there transfer into light emission with a particular wavelength. So grosso modo, it means that the light color corresponds to the gap. So choosing the right material should allow us to tune the light the light source that we want. So, and here is where GaN appears in the scene and adds value to the lighting industry. So So GaN appeared in the semiconductor scene when the industry was in search for material emitting in the blue range. That was by the 60s, 70s last century. And the main purpose was to obtain white illumination. At the time, there were already LEDs in red and infrared, but particularly for illumination, there were red and green sources, but there were not blue ones. It was missing for quite some time. And GaN comes to the table because it turns out that the emission characteristics of GaN and some other GaN-related materials allow it to emit or generate emissions in the blue range. So, but though the material answer was here, process-wise, it was extremely difficult to obtain actually this blue LED. So the use of GaN for blue LEDs revolutionized the display industry. And as those who were born like the 70s, 80s, 90s, it allowed the development of the Blu-ray related to CDs and DVDs. Some people are not familiar with that anymore. But what happened later with the increasing demands on image quality, on power efficiency? Well, the transition from RGB illumination was towards white light. So, so in a way, the development of the blue LED, let's say, revolutionized the lighting technologies. Because if you can produce white, we have that white light is more efficient when it comes to conversion from the power lines. Around 50% of the actual energy becomes light, compared to 10, 12% of the old incandescent bulbs. So basically the incorporation of GaN to the LEDs and to some other devices and in lighting technologies has helped reducing dramatically the world energy demands. So still nowadays there are many efforts concentrated on enhancing the devices, the GaN-based devices for white sources. Well, what we see here on the left, it's an example of a more realistic and complex configuration of a white LED. We can see below its emission spectrum with two peaks, a blue at 460 nanometers and a yellow at 560. What is curious here is we have a combination of gallium nitride emitting diode here on top, and with other, let's say, secondary color generated by phosphorus around the original LED. So, and what you see here on the right, let's say it's a table. We find a palette of compound semiconductors used to obtain different LED colors. Well, an LED color, the relevance is tremendous in communication, in material processing. It's not a fashionable thing only. So here I would like to mention that, let's say, when GaN was incorporated into LEDs, is when scientists found the biggest challenges. The biggest challenges, and what it was about. It was about crystal growth. It was very difficult. It took 50 years at least to be able to grow high quality gallium nitride crystals. And yeah, you still need to grow them in a particular substrate. So you cannot, for GaN, you cannot have this homoepitaxial growth. So LED industry dealt with most of the challenges associated to growing GaN. And with these challenges partially, let's say, solved by around 2002, the attention of the industry, of other industries, moved towards GaN. For example, the military industry has a lot of interest in power GaN transistors and RF transistors, given the electrical, let's say, the good electrical properties of the material, despite the difficulties growing the crystal. So, well, we bring this to attention because then we have, well, we're coming back to the electrical part of GaN and the electrical properties. So we have, again, that GaN has a wider bandgap than silicon, comparable electron mobility, relatively similar thermal conductivity, and a way bigger breakdown electric field. So what does it mean? You can operate GaN devices at higher voltages, nearly similar thermal conditions, but also, well, you can have way smaller devices when you consider the breakdown electric field. So when we come to, well, to look why those properties are important for transistor, well, we look at a transistor because at a basic level, a transistor is a 3-layer PNP or NPN semiconductor device with 2 junctions. And there are, well, the main functions of these transistors are to amplify electrical signals and to switch. So, well, as for amplification, I mean turning small electrical signals into larger or more powerful ones. And as for switching, it basically acts as a microscopic switch, allowing current to flow through, only to flow through only at specific times. So for both functions, amplification and switching, well, the frequency at which the transistor can switch off and off is directly influenced by the, let's say, easiness at which the electrons in the materials can go from the valence to the covalent band and vice versa. So in a way, intrinsically, the bandwidth levels define the capabilities at which you can stimulate the shift of the electrons in the bandwidth. There are many other variants related to how easy or can, let's say, how fast can a transistor switch, and it's mostly related to the architecture and many other phenomena in the surface in between materials. Well, just to mention here that on a broader scale, the major families of transistors are BJTs and FETs, so bipolar junction transistors and field effect transistors. So, but irrespective of the family that they belong, all transistors have proper specific arrangements of different semiconductors materials. Basically, we classify them depending on their structure, and each one has its own characteristics, advantages and disadvantages. Well, physically, structurally, the differences between BJT and FET is in BJT, both majority and minority charge carriers are required to operate, whereas in the case of FETs, only a majority charge carriers are required. But, well, the message here is basically that irrespective of the family, well, all transistors have really customized, proper, specific arrangements depending on the application. It would be way too ambitious to describe all the different variations and configuration and architectures of the map of transistors for power and RF. Well, then GaN for power transistors. So power transistors are one of the primary contributors to the power loss in the switching systems. And the losses come generally from conduction and switching. So the conduction losses are those caused by current flow when the transistor is on, and switching losses occur in the transitions between on and off states. When on, GaN transistor resemble a resistance between the drain and source, often referred as R-on. So the point here is that on resistance is one of the main parameters to define the quality or the performance of a power transistor. So there's a benefit. These are on. So the conduction losses are proportional to the on resistance. So there are benefits. There are benefits of GaN and the other materials. 1 second, please. Okay, so coming back to the graph. A benefit of GaN and other wide bandgap material is that the relationship between the breakdown voltage and the R-on shows that the theoretical limit of, just 1 second, please, I'm struggling with something here. Okay, I was saying that there are benefits because there is a relationship between the breakdown voltage and the R-on of this material. As we see in this figure, we have the theoretical limits for this relationship for silicon GaN and for silicon carbide. Silicon GaN and silicon carbide. We can see that for a given breakdown voltage, the R-on of these materials is much lower than for silicon. And we have that GaN is the lowest of the three. Well, a silicon has basically reached its theoretical limit. The use of GaN and other wide bandgap materials has become necessary to improve the R-on. Well, there are other factors that contribute to this, to switching losses, and several of them are improved through the use of GaN. So one of the loss mechanisms there results from the fact that the current in a transistor begins to flow before the drain source voltage begins to fall. And well, during the time of the fall, I'm missing the graph here, but probably you're already familiar with it. During the time of the fall, the losses are very large. So if you increase the speed at which a switch turns on, then you will reduce the losses during this transition. So as we have that GaN transistor are able to turn on faster than silicon transistors, then we will have as a result that they are able to reduce the losses. If we come into the details of the operation rate of power transistors available, well, we will find zones or ranges of application where different materials and different types of transistor compete. In general, applications that require higher frequencies and middle low power, we have that GaN as a very good option here. I'm just showcasing the data centers case and some consumers applications. So in comparison, silicon carbide, so it's better for middle range frequency applications. And then when we need higher powers, but when we need higher powers, around 100 kilowatts, between 10 and 100 hertz, but when we need higher powers, we need to move, let's say, toward smaller frequency, where we have the traditional IGBTs. We see here the MOSFET, but I will not comment on them. They are the, let's say, the standard for many applications in industry. Here I will come briefly on the, we have a very similar, resembling a graph for the RF transistor. So basically GaN-HEMT, let's say, when one analyzes this, the Johnson's the Johnson graph for different materials used for RF application. Let's say one can select a range of frequency. Let's say you need to compromise in different aspects. And what we have finally today is basically GaN-HEMTs operating at 3 gigahertz and above, moving towards higher power efficiencies. If we take a look at the industrial landscape, well, our colleague from the first webinar shared and described in detail this panorama of the power GaN value chain. So if you see, well, you have big players here. You have basically the foundries, producing GaN are currently Innoscience as let's say the biggest player, I believe, right now. This graph is very dynamic. We have TSMC, XFAB. We have also plenty of integrated IDMs, integrated device manufacturers like onsemi, Infineon, Transform. Since the last time, it's probably that let's say there have been different acquisitions. And we will have that there are certain similarities with the GaN for RF value chain. So it's a quite related, it's a quite mixed ecosystem. As let's say GaN market is still building up. It's not a steady market or as solid as silicon. Well, in terms of GaN device market, it is the consumer applications which lead it, starting mostly by fast chargers, followed by data centers and automobile onboard chargers, also moving towards industrial and power voltaics. On this, I would like to mention that it's been already since 2018 and even before that GaN devices are used in DC-DC converters in chargers for, well, this is probably for Apple chargers, many Apple chargers, or but also to the day, and I mean December, November last year, GaN devices starting to be part of smartphones. That it was announced by Innoscience. So let's say that well, the GaN device market is growing. It's very interesting to see the projections for 2027, as you see here from the Yole report. And we see a growth in the automotive and the mobility sector as well. And big hopes are, let's say, I put on the data center part. What about the GaN roadmap? Well, in order to increase GaN participation in the market of power electronics, there is a transition on the wafer size, going from the 2-inch to the 12-inch wafer, that it's under development, and it's of big interest in order to reduce the costs of fabrication. Technologies are aiming to reach higher breakdown voltages This is addressed via development of new substrates to deal with thermal management with monolithic integration, and also via different device architectures. This is a rather not so new GaN RF device market graph. This is also corresponding to YOL. But what has been happening is that what we can see here is that the telecom infrastructure is the biggest consumer, the biggest customer for RF devices on, let's say, well, apologies, it's the second, but then we have the military. Actually, they were the ones who started with the interest for the communications. So the trend tends to be kind of the same, and it continues to grow. The faster transistor, the more effective communications we can have. The demand is increasing, not just for military, but in general for all our communications. And there are a few niches there where there's a competition with gallium arsenide. For this, you can refer to the episode number 4, where there was a, let's say, in-depth description of how gallium arsenide devices are impacting RF industry. We also have that in the consumer segment. Well, gallium arsenide and GaN are, they are disputing the market, and also in base stations. Finally, this is a rather different slide, and this is from the micro LED market adoption. So in this case, this is not a map of the ecosystem, but let's say how this is about how different industries have adopted micro LEDs, which is, let's say, a latest development of the LED industry. Many of these devices are already elements that we have in our daily life. They are part of the consumers that we use every day. So the point here is that this is already happening. This is nothing. This is nothing new. It's just happening. GaN adoption is a fact, and it's already in our everyday devices. Having briefly checked the technical and industrial part of GaN for these technologies, I'm moving to show how GaN what GaN offers and what GaN platforms exist for your practice. So currently, your practice, there are 2 fabs that offer access to GaN. In one hand, and in alphabetical order, we have an imec platform that is GaN on SOI for power integrated circuits. And there, 2 processors are offered, 200 volt and 650 volts. You can access these offered via multi-project wafer services. And on the other hand, you have UMS. We have UMS, well, where the speaker of a previous episode, he dug deep into this offer. But overall, you can have access GaN to have access to. You can have access to GaN processors for power, and also to gallium arsenide processors for RF. So if we look at those offers a little bit more in detail, we start with imec. The offer of GaN, at least via MPW, is GaN on an SOI substrate, which has been imec's approach towards true monolithic integration. The technology uses buried oxide combined with trench isolation, and this way the substrate is connected to the source side. So that way each transistor gets its own isolated pocket. As mentioned before, the PDKs are available for 200 and 650 volt technologies. And there have been, there are RDL models that allow customers to, let's say, to address the type of package that is more convenient. So for some tests, wire bonding may work better. Some customers want to design a package via flip chip. Apologies, the cursor is not working very good. So to give you an idea of the scope of applications achieved with this technology, I'm showing you here a couple of demonstrators manufactured by our clients between 2022 and 2023 via the MPW. So on the left, you have a 200 volts monolithic half bridge. It was fabricated in the frame of a public project for space applications. If you look at the dimensions of the integrated circuit, it's around 6,000 micrometers by 3,000 micrometers. And you can notice, well, maybe not from the graph, but around 30% of the chip is dedicated to the gate drive. So, and this is quite a complex and very, very impressive circuit. If we come to the right side, the second demonstrator is a high efficiency totem pole PFC converter developed by the Leibniz University of Hanover, and it was fabricated on the 650 volt GaN-SC MPW shuttle. Also, as you can see, there's a lot of complexity in this device. You have the logic and the power all together in an area of 5 by 2.5 millimeters. So this is these are some of the let's say most impressive designs we have been working. I must comment here also that broadly the attempts that we have seen without compromising information are towards half bridges and a lot of control circuits. So technically, this is very advanced, and it's moving towards industrialization. On the other hand, we have UMS offer with their process G25 and G15 for GaN HEMT for power, as well as their process P10, which is for gallium arsenide low noise HEMT. As they described also in the previous session, they do have some demonstrator. They have qualified transistor, a qualified offer, and they seem to have a very stable cycle time for their fabrication. So you can address UMS for more information about their offer. Additionally, also, if you have some questions about the circuits that we show also for GaN, just feel free to send them. We can put you in contact with the persons responsible for the designs. So in summary, we have the GaN growth enabled the development of blue LEDs and related illumination technologies, very, very relevant. We have the GaN is a compound semiconductor that speeds up the performance of power conversion and power switching technologies, just starting from the perspective of material processing. GaN devices are already commercialized for power, RF, and illumination, and the participation in the market continues to grow. There are technical challenges associated to GaN, in the part of the crystal growth, in parts of thermal dissipation, that what we didn't talk. But at the end, these challenges reflect so far in a slower adoption in the market, dominated by silicon components. They're not the only reason, I would say, but they are quite defined from a material perspective. And finally, we have GaN on SOI platform for power electronics, and also gallium and gallium arsenide platforms for power RF, accessible via the MPW services offered by Europractice.